For the next two sets of descriptive statistics, we move away from the geometric pattern of the points as such and focus on the intensity. And first of all, we consider quadrat counts. And quadrat counts really try to assess the degree to which the intensity is constant across the space. So remember, the intensity of a point pattern is the number of points divided by the area. So the rationale of quadrat counts is to take some area and superimpose it on the points and then compute whether the intensities, so the ratio of the number of points in each quadrat over the area of the quadrat, is constant across the space. So it's a very simple procedure, but it has a number of drawbacks and uncertainties associated with it. First of all, the quadrat is a polygon. Well, what should it be? Should it be a circle, a square, a triangle? Typically, in the classic approach, the quadrants are grid cells in a rectangle. So one superimposes a rectangle on the point pattern, counts the number of points in each of the boxes, and then computes or visualizes the intensity. It's a very basic procedure. And let us illustrate this for the Chicago example. Remember, there was the lake, and the lake didn't have any stores in it. So on the left, we have a traditional quadrant count grid with 3 cells in the horizontal dimension and 6 cells in the vertical dimension. And each of these cells gives the number of points in that cell. On the right-hand side, we take a slightly more complicated approach where we superimpose the grid cells on the actual physical boundary of the city. And then again, in each of the resulting polygons, we count the number of points. And so this reflects the unevenness of the distribution of the points. Now, a better way to visualize it, especially for the irregular polygons, is to create a so-called quadrat count intensity graph, which is essentially the same information as before, but rather than presenting the counts as such, we convert the counts into intensity measures by dividing them by the area of the polygon that they're in. And if you look very carefully, the yellow area in the upper right is not the area with the most points in it, but it's a fairly small area, and so therefore the intensity as the ratio of the points over the area is much higher than elsewhere. So this is again a very cut and dry summary of the point pattern, and it has been used as an actual test statistic to test the null hypothesis of constant intensity. So the rationale is the following. If there is a constant intensity throughout the region, then the counts in each of the boxes, especially if the boxes are of equal area as they are in the grid example, these counts, they can vary a little bit, but not too much. And so the test statistic is constructed to assess the extent to which any deviation from uniformity is compatible with the null hypothesis. And it is constructed as a very classical chi-square test. So chi-square test looks at the difference between the observed counts and the expected counts. So first of all, to do this, we need to have a measure of what are the expected counts. And so what could we expect on average as the count in each of the cells in the grid boxes? And a most straightforward way to do this is to take the total number of points and divide them by the number of grid cells, the number of subregions. And this gives us what, under a null hypothesis of constant intensity, we could expect the count to be in each of the cells. So then in the classic chi-squared approach, we take in the numerator the sum of square deviations of the actual observed counts in each cell minus the expected cells, and we divide that by the average expected. So classic chi-square test, the number of degrees of freedom is the number of cells, m minus 1, y minus 1, because we already ate up, so to speak, 1 degree of freedom by computing the mean, the expected number of points in each cell. And it's a very traditional chi-square goodness of fit test. There's been some discussion in the early literature about the appropriateness of the chi-square as such, and so an alternative is to carry out Monte Carlo inference, which is a procedure in the usual fashion. We just simulate the pattern under the null hypothesis of constant intensity and then compare that to the actual observed pattern and recompute the chi-square test multiple times and then assess whether the observed value is extreme relative to this reference distribution. We'll revisit this rationale later when we talk about spatial autocorrelation as well. So what does this look like for our example? If we have, again, our 3 by 6 set of grid cells, in each of the cells we have 3 values. We have the observed count, for example, in the upper left corner, we have 8 points in that box. The average to be expected is 149 divided by 18, which is, there's 18 cells, so that's 8.3. And then we take the difference. If you carry out the full computation, the result is something like 167.9 with 17, that's 18 minus 1 degrees of freedom, and it's highly, highly significant. So we strongly reject the null hypothesis that the intensity is constant throughout this space. This is a very quick and dirty test, but it has its problems, one of which I already alluded to is the arbitrariness of the selection of the quadrant. What is the polygon? Should it be large? Should it be small? This gets us back into this modifiable areal unit problem we talked about in the first module, scale issues. So are the results the same when you use 3 by 6 versus 5 by 10 or some other grid size? The square grid is an obvious choice, but should it be square? Could it be rectangle? Could it be circle, irregular polygons, as we illustrated with the map of the Chicago boundary. Another aspect that we haven't really touched upon is, should the polygons, the containers, be fixed as they are in the examples that we used, or should they be randomly spread over the landscape? So you take 18 squares, you randomly throw them over the points, and you count the points in each of the squares. That's another discussion. But most importantly, the test statistic as such ignores the fact that the counts in nearby grid cells may very well be spatially correlated, may very well be more similar than they would be randomly, and that will affect the inference. So inference could be spurious in the sense that your p-value, your type 1 error, is actually not what you think it is from the computation. So this is Quadrat Counts, a very a discrete approximation, if you wish, of the variability of the intensity throughout the point pattern. This contrasts with intensity functions or kernel functions, or also called heat maps, which are actually a continuous way to assess the variability of the intensity throughout the point pattern. So an intensity function focuses on spatial heterogeneity, how the intensity of the process, so the number of points per area, varies with a location in the region. And this requires a non-parametric estimation of the intensity. So in contrast to the Quadrat counts, where we impose a discrete set of subcells, so to speak, and then estimate the intensity in those and then possibly map it. Here we take a continuous approach and use a non-parametric kernel function to estimate the intensity function. And it's important to point out, and this is a common source of confusion, that there is a difference between the intensity function that is used in point pattern analysis and a density function that is used in standard statistics. It's not a major distinction because they're basically the same but rescaled. And the difference is that an intensity function follows the definition of intensity that we've already covered. So it gives the expected number of events per unit area at any given location. So if you integrate this function, it is like a density function, but unlike a density function, the integral has to do with the overall number of events, is not 1. A density function is a probability of an event, and so that integrates to 1. So the difference between the two is that they basically give a different magnitude, but they will have the same overall shape. So intensity function has to do with the expected number of events. A density function has to do with the probability of an event. So basically they are rescaled versions of one another. Kernel density estimation is a non-parametric approach. It's basically a weighted average, a weighted moving average of the data, where you move a kernel. A kernel is a particular function. You move the kernel over the data and compute its value at each location, and then summarize that in an overall function. And the kernel function, you can think of it as if you position the function, and I'll show a visual illustration in a second. If you position the function at a given location, let's say u, then you take the difference in distance between that point u, you take the distance between that point u and any other point u sub I that is within the bandwidth. And the bandwidth is the range of computation. Let's say you would take a simple average and you have a point, and you have 4 points within, say, 5 units of distance. The bandwidth would be 5. The 4 points would be the 4 i's that you count, and the k would be average. So then that would be a very simple uniform kernel function where you take the values at these 4 adjoining points and summarize them in the kernel function. And then you assign the value of the kernel function to location u. And then you move the kernel over to another location and repeat the same process. So there are two important components, aspects to a kernel density estimation, or in our case, a kernel intensity estimation. One is the choice of the kernel function specifically. In my example, I used a uniform, but typically a kernel function implies a distance to k, so that points that are further away from the reference point have less weight than points that are closer to it. That's the first aspect, the kernel function. The second aspect, which is actually more important in terms of sensitivity analysis, is the bandwidth, which is how far out you go to take neighboring points into account. So let me illustrate this with a very nice graph that I borrowed from the CrimeStat manual, and I really think it shows the principle. And so what we have here, the little red balls are the points. It's in one dimension just to illustrate the concept. And over each of these points, we have a bell-shaped curve. And let's just, we'll see later, this is a Gaussian or a normal kernel. So then we center each of these nice little bell-shaped curves over the point, and then add up the values for whatever curve is above that point, and that results in the blue line, and the blue line would be the kernel density estimate. And so what we see in this particular case is that we get a peak over the 3 points, because that's where most of the value is added together. Then it goes down in the gap between the 3 and the 2 points, and then there's a little bump over the 2 points. Okay, so the principle is you have this kernel function which basically moves over each point, and then the kernel is the summation of all these individual functions. They're added up together or averaged, but it's the blue line is the combination of the red lines. And if we change the bandwidth and make it narrower, as in this graph, you see the effect on the kernel function. So now we still have a bell-shaped curve centered on each of these points, but the bandwidth is much smaller. So we get a much higher spikiness of the kernel density or the kernel intensity, and we get a spike over the 3 points and then another spike over the 2 points. And so kernel intensity estimation is very sensitive to the choice of the bandwidth, not so much to the choice of the kernel function as such. In point pattern analysis, the typical kernel function that's used is a Gaussian or normal distribution. Now, a normal distribution is actually infinite. The bandwidth is not a hard cutoff point. And the convention is to use the standard deviation in this expression B as the bandwidth. So with a larger standard deviation, your bell shape will spread out further. With a smaller standard deviation, it will be spikier, as we illustrated in the previous graph. There's actually 5 or 6 kernel functions in common use in statistics. The triangle one and the quartic one are some other examples, but typically in point pattern analysis, one sees the Gaussian one used. And to illustrate this for our Chicago example again, this is a Gaussian kernel that uses a default bandwidth suggested by the SPATSTAT software that we'll be using in the lab. So if you just take the standard default, the bandwidth is 14,000, and remember these are feet given the particular projection that we use. But you see the point. This is what we call a heat map. The brightest part is gives the location of the highest intensity of points, and you see the intensity decreases as we move away from the near north side of the city, and then it goes way down when we go to the south side. And the little part on the upper left is actually O'Hare Airport, and there's nothing there in terms of supermarkets. So that's the idea of a heat map or a kernel density. It's a very nice visual summary. It's actually very popular in visualization, in several cartographic packages and GIS packages include this. To illustrate the effect of the bandwidth, here rather than 14,000 we have 6,000, which is, as we'll see in the lab, one of the optimal bandwidths using a different criterion. And you see the distribution is much spikier, is changed quite a bit. We, rather than a uniform blue in the south side, we have a little pink area in the lower left side, and we have also a much smaller yellow area at the core of the density of the points. But basically, the same general impression is given of a higher density, higher intensity in the northeast of the city, and then much lower density in the outskirts and especially in the southern part of the city. So this is the idea of a kernel intensity function. It summarizes the intensity or rather the variability of the intensity in the point pattern, but in contrast to Quadrat Counts, which is a discrete approximation, the kernel function approach is a continuous approximation. And this closes the discussion of the descriptive statistics in this module.